Hi, my name is Eloise.
Got you. Oh, hey there. I'm here and I'm ready to learn more about functions. So what are you going to do today?
Good to have you back with us. Today we are going to carry on looking at changes to the linear function. We are going to need some of our knowledge from the previous lesson, so do you remember what we did last time?
Let's see. It's here somewhere. Oh, last time we saw that linear functions have the formula y equals ax plus q, where a shows the gradient of the straight line graph and q shows the y-intercept. We wanted to see how the graph changed when we changed the gradient, so we decided to choose the linear function y equals x as the parent function, and we called its graph the parent graph. This helped us to compare graphs that have different gradients to each other. We made q equal to 0 for all these graphs. By comparing the graphs, we discovered that by changing the a value of the formula, we would make the gradient or the slope of the graph become steeper or flatter.
Good! Now in this lesson we want to see what effect the q has on the graph. By the end of the lesson, you should be able to describe the effect of changes in the q value on a linear function and describe the change in the parent graph caused by a change in the a and q values. In our previous lesson, we chose the y equals x graph as the parent graph, so let's start with that again. This time, we are going to keep the gradient the same for all the graphs we look at. That means that in the formula, we will keep the value of a the same. This way we can focus on the changes to the value of q. The gradient of the parent graph is a equal to 1, so let's keep a gradient of 1 for all our graphs. Now I'm going to move the parent graph. Let's see what happens when we do this. If I shift the graph up 1 unit like this, what do you think the formula of this new graph will be?
Well, it's still a straight line, so the formula must be y equals a times x plus q. So we need to find the gradient and the y-intercept.
Okay, and what do you think they are going to be?
The y-intercept is easy. It's 1.
Right. Q is 1, so we just need to find the gradient.
The gradient doesn't change, so it stays 1. Which means that the formula of the line after the shift is y equals 1x plus 1.
Well done! So when the parent graph is shifted 1 place up, the new graph has a formula of y equals x plus 1. Now let's go back to the graph of y equals x. How do you think the formula will change if we now shift the graph 2 positions down, like this?
This shouldn't be too difficult. The y-intercept is -2, so q is -2, and the gradient is again 1. We kept the slope of the line the same and just moved it down.
That's right. So we get the formula y equals 1x minus 2. Now I want you to have a look at all the graphs that we have done so far. The parent graph y equals x, the one that shifted up, and this one that shifted down. Do you notice anything interesting about them?
Well, the 3 graphs kind of look like they could be parallel to me.
And why do you think that is?
Is it because they all have the same gradient?
Yes, the gradients are the same, but how can you be sure they are parallel? What makes lines parallel?
I think I've got it here in my toolbox somewhere. Let me check. Where is it? Here. Parallel lines are lines that are the same distance from each other. Perhaps you can check that on these lines. It shouldn't be too hard because we can use the blocks of the grid to help us.
Okay, explain to me how you would do it.
If I count the blocks along the y-axis, the distance between the parent graph and the x plus 1 graph is 1 block. And the distance between the parent graph and the x minus 2 graph is 2 blocks.
Yes, but remember, if we want to prove that the lines are parallel, we must make sure the graphs are the same distances apart anywhere we look. Here, where x equals 0, it is easy to see the distances between the parent graph and the shifted graphs.
Sure, but it's still the same where x is 3. Look, the distances between the lines are still the same. 1 between these two and 2 between these two.
You are quite right. It will be the same at any point we try. At any x along here, the distances between the lines stay the same. An important thing to remember is that the gradient of a straight line doesn't change. So the lines won't change direction, and the distances between them will also not change.
I think I understood what we did, but can we go over it again? Just in case, I could have missed something.
Sure. First we started with a parent formula. The one we used was y equals x, where the gradient was 1. So the value of a in the formula remained unchanged at 1. The only other thing in the formula that could change was the q value. Then we compared two different graphs to the parent graph. In this graph, the q value was 1, and in this graph, the q value is -2. Let's look at this in a different way. If I give you the formula for a linear graph, can you work out how the parent graph would shift to make the new graph?
I'll give it a go.
Okay, here is the formula. Y equals x minus 4. How does the parent graph shift to make this graph?
Give me a moment to draw the graphs. There we are. The gradient is the same as for y equals x, but now the graph cuts the y-axis at -4. So we shift the graph down 4 places and we keep it parallel to the parent function.
Well done. So -4 shifts the graph down 4 places. In your new graph, it's as if each point on the parent graph has dropped by 4 units. So to recap what we have seen here, if the graph of y equals x shifts up or down q places, each y value on the parent graph will be shifted up or down q places on the new graph. And the new graph will have a formula of y equals ax plus q.
But how will I know if the shift is up or if it's down?
That's not too difficult. Let me show you. If the q value is positive as it is in this graph, the shift will be up. If the q value is negative as it is in this graph here, the shift will be down. A positive q value shifts the graph up by q units, and a negative q value shifts the graph down by q units. Now we can work with any linear graphs by changing the parent function y equals x. If the slope of the graph is steeper or flatter than the parent graph, then the a value or the gradient has been changed. A shift of the parent graph up or down the y-axis means a change in the q value and the y-intercepts. Of course, many graphs are made by combining changes in the gradient and shifts of the parent graph. In the formulae, we can see a change in both the gradient and the y-intercept.
So let me see if I get this. You're saying there's a graph where both the a and the q value have changed.
That's right. You look a bit puzzled, so let me show you what I mean. How do you think we would change the parent graph y equals x to make the graph of y equals 3x minus 2? In other words, we want to describe the movement of the parent graph y equals x that will make this new graph.
One bit at a time.
Well, for a wild guess, that's a pretty good answer. First, we are going to look at how we must change the gradient of the parent graph to get the gradient of the new graph. Then we are going to see how we must shift the parent graph to reach the y-intercept of the new graph. Here, I'll show you. Watch how the parent graph is changed to create the new graph of y equals 3x minus 2. Let's look at it again and describe the change. The gradient of the parent graph y has been made steeper. So the new gradient is 3 over 1. Then the graph shifts down 2 units to make the y-intercept minus 2.
Does it matter which change we do first?
We prefer to show changes caused by the a value first and then the shift caused by the q value afterwards. Doing it in this order makes things easier when we deal with other functions.
I'm all for easier.
Okay, do you think you are ready for a task?
Yeah, I think I've got this.
Question 1. Describe the changes to the parent graph y equals x if q equals 3. Then draw the new graph. Question 2. A linear graph has a formula y equals negative x plus 3. Describe the changes to the graph of y equals x to make a graph with the formula y equals negative x plus 3.
Those look a bit hard.
Not really. If you think of any linear function as a change of gradient and a shift up or down of the parent graph, then the differences in the formula make sense. In the next lesson, we are going to look at the formula and the graph for the quadratic function. Again, we will look for what causes the differences in the graphs.